So this class is the continuation of class 7 of CNS. So in this chapter we will discuss about the Euclidean algorithm to find out the GCD, and also the extended Euclidean algorithm to find out the multiplicative inverse of two numbers. So that will be applied on a Galois field. So here Euclidean algorithm to find out GCD and extended Euclidean algorithm to find out multiplicative inverse in a Galois field. So first we will discuss about the the Euclidean algorithm, and then we will discuss about the extended Euclidean algorithm. So the GCD is a common problem in number theory, as you know. The GCD of AB is the largest number that divides evenly into both A and B. So example, GCD of 60 and 24 is equal to 12. That means 12 is can divide 60 and 24 both. Often we want no common factor except 1, and hence the numbers are relatively prime. So when the GCD of two numbers and GCD of two numbers are 1, then we can say that this A and B are relatively prime. Relatively prime. So here 8 and 15 are relatively prime. So now, and this is the Euclidean algorithm. It is an efficient way to find GCD of two numbers using the theorem that GCD of AB is equal to GCD of B, A mod B. A mod B. Okay. So Euclidean B is A is equal to A and B is equal to B. If this B is equal to 0, then it will return A. So as the GCD. So GCD of A and B is equal to capital A. Yeah. If that is not equal to 0, then we have to calculate the remainder. Then we have to do this process, and we have to go to check whether B is equal to 0 or not. So when B is equal to 0, then it will be A will be the GCD, capital A will be the GCD. So this process will be repeated until we are calculating the GCD, whether it is 1 or any other number. So this is a recursive function by using which we can calculate the GCD of A and B, two numbers. Let's see, calculate. So here, suppose let's say find GCD of 54 and 24. So here A is equal to 54 and B is equal to 24. So we have to arrange in this way so that always A is more than B. So if vice versa, if reverse, A is less than B, then A will become B and B will become A. We have to perform some swap operation here. Okay, so as per the algorithm, what we have to do? We have to find out capital A is equal to A, then capital V is equal to small v, and let's see, that is A, B, and R is the remainder. R is the remainder. So here A is 54, B is 24. So this is step 1. So based on the algorithm, that is, if B is equal to 0, A is the GCD of A and B. So here B is equal to 24, so that is not equal to 0. So that we have to calculate the remainder. So remainder is 54 divided by 24, that is 48 divided by 6. So the remainder is 6. So this is the remainder. You have to repeat the process next, that is not equal to 0, so that A will become 24, B will become 6. Okay. Now here we have to check B is equal to 0, A is GCD of A. So B is equal to 6, that is not equal to 0. So we have once again we have to calculate the remainder here. So the remainder will be 24, that is now 0. And we have to set 6 and that is 0. And go to step 2. If B is equal to 0, A is GCD. So now B becomes 0. So A is, the value of A is 6. So GCD of 54 and 24 is equal to 6. So this is the process by using which we can calculate the GCD, greatest common divisor, of two numbers. Okay. So I think you have understood this very simplest algorithm to calculate the GCD. Next. Okay. So this is the expansion. Yeah. So 170 we can write that the modular reduction method, that is 1 into 1066 plus 905. Okay. So then it will become this. So we can write 904 comma 162. So next, so repeat. So when it is 0, then GCD will be 2. Okay. So next is the Galois field. The finite fields play a key role in cryptography. Can show number of elements in a finite field must be a power of any prime number P. Must be a power of any prime number P. So the number of elements in a Galois field is must be equal to a power of a prime number. So known as a Galois field, denoted by GF P to the power n. In a particular, often we use the field GF Galois field of P and Galois field of 2 to the power n. The Galois field, the set of integers 0 to P minus 1. That means already we have discussed that is Galois field of P. That means P to the power n number of elements are there, with arithmetic operation of modulo prime P. Okay. The Galois field is the set of integers with arithmetic operation modulo prime P. These form a finite field since have multiplicative inverses. Since it has the multiplicative inverse, hence it is called a finite field, and hence arithmetic is well behaved and can do addition, subtraction, multiplication and division without leaving the field of the closure. Without leaving the closure property, we can perform addition operation, subtraction operation, multiplication operation and division operation. Okay. So to find out the multiplicative inverse in case of a Galois field, we can use the extended Euclidean algorithm. Extended Euclidean algorithm. Let's see what is multiplicative inverse. Multiplicative inverse means B dot B inverse is equal to the identity. That means if B is a number, so suppose this is the Galois field of prime 7. 7 means there are 7 digits are there, 0 to 6, 7 numbers are there. So Galois field 7, that means the number cannot exceed 6, because this is the base is 7, or we can say that this is the Galois field of 7, Z7, Z subscript 7, Z subscript 7. So we can select a number between 0 to 6, and if we are able to find the inverse of that number, okay, so that B dot B of inverse is equal to 1, then it is known as the multiplicative inverse. So here B inverse is known as the multiplicative inverse, and both B and B1 must be present in Z7. Inverse must be present in Z7. Okay, so here we can find 1. If 1 will be multiplied with 1, then it is giving 1, the multiplicative identity. So if we are multiplying 2 with 4, it is giving 1. So the multiplicative inverse of 2 is 4 in Z7, right? So similarly, the multiplicative inverse of 3 is 5, because here 3 is multiplied with 5 to give 1. So 5 multiplicative inverse of 3 is 5 in Z7, because here 3 and 5 multiplied, it will be that means B inverse is equal to 1. So here 4 to 8, so 4 vice versa. Then 6 is multiplied with 6, that is given. So multiplicative inverse 6 is 6 in case of, that means here 6 into 6 is equal to 36. 36 mod 7, so 1. So the result is 1. So that is given, that is modulo 7. That is modulo 7. That means here this is okay. So this is the extended Euclidean algorithm. M and P to find out the multiplicative inverse of P. So what is M? M is the base or the prime number, or the subscript of the Galois field, base of the Galois field, or the prime number, or we can say that is the Z. Okay, that means here find the multiplicative inverse B in Zm. So this is you have calculated the multiplicative inverse of B, that is B inverse in Galois field of Zm. So let's see. Okay, so what we are doing here, extended Euclid M and B. So this is the initial declaration. So we have to consider these values. Let's say A1 is A1, A2, A3 are 10 M. A1, A2, A3 is 10 M, and B1, B2, B3 is 0, 1, B. If B3 is equal to 0, then return A3 is the GCD, and no inverse is present. If B3 is 1, then B3 is the GCD. That means M and B are relatively, prime, and B2 is the B inverse. So what is B inverse? B inverse is the B2. If it is not possible, that means here, if B3 is equal to 0, A3 is the GCD, no inverse is possible. If B3 is 1, then B3 is the GCD and B2 is the inverse. So if that is not true, then Q, that is the quotient, is equal to A3 divided by B3. A3 divided by B3, and then T1, T2, T3 is A1 minus Q B1, A2 minus Q B2, A3 minus Q B3. So here we have to do some swap operation. A1, A2, A3 is equal to B1, B2, B3, and B1, B2, B3 is T1, T2, T3. Go to step 2 and repeat this process until either the B3 is 0 or B3 is 1. So we have to do that. Okay, let's see. Let's see. So here we are going to calculate GCD of M and B. GCD of M and B. So from this, so M is the field Galois field base, the prime number, and B is the number where we have to find, and we have to find B, and that is B is given, M is given, and we have to find this. So what we have to do first, initial convention. So step 1, we have to find A1, A2 and A3, that is equal to 1, 0 and 1, 0 and M. So A1 will be 1, A2 will be 0, A3 will be M, and B1, B2, B3 is equal to 0, 1 and B. So B1 is 0, B2 is 1 and B3 is B. So in step 2, what we have to do? In step 2, sorry, this is not GCD. This is extended Euclid. Extended Euclid to find out B inverse. Simultaneously also it can calculate the GCD. Yes, if you write that, there is no wrong. But this algorithm is extended Euclid. Then if B3 is 0, if B3 is equal to, sorry, if B3 is equal to 0, then GCD of M and V is equal to A3 and no inverse is present. If this is true, remember this. And step 3, if B3 is equal to 1, then B3 is equal to GCD of M and V. That means M and B are relatively prime. Relatively prime. If this is not true, otherwise step 4, otherwise if this is not true, this is not true, then we have to calculate Q. Q is equal to A3 divided by B3. Quotient Q is equal to A3 divided by B3. Okay, slicing the fraction. Only the integer part we have to take. A3 divided by B3. Then T1 temporary variables, some temporary variable T1, T2, T3, that is A1 minus Q B1, A2 minus Q B2, A3 minus Q B3. Okay. And now A1, A2, A3 is equal to B1, B2 and B3, and B1, B2, B3 is equal to T1, T2 and T3. Okay. So after doing this, you have to go to step 2, repeat this process, repeat this process till you are getting either 0 or that is 1. Next, one question, find how to solve a problem. Find the multiplicative inverse of 11 in the Galois field of Z26. Okay, so here, so find the multiplicative inverse of 11 in Z26. So here, extended Euclid, that is M and V. So here, that is we are calculating 26 and B is 11. So 26 and 11. So M is 26 and B is 11. So we have to find out B inverse. Right, let's see. So A1, A2, A3, B1, B2, B3, T1, T2, T3 and U. Okay, so T1 is equal to how much? So we have it already, that is A1 minus Q B1, A2 minus Q B2, and that is A3 minus Q B3. Okay, so A1, A2, A3, A1, A2, A3 is, let's say, A1, A2, 1, 0 and M, B1, B2, B3 0, 1, B. So that is 1, 0 and that M is 26. B1, B2, B3 0, 1 and that is 11. So this is the first step, right? So next is, if if B3 is equal to 0 or 1, if B3 is 0, then A3 is the GCD. If B3 is 1, then B2 is the inverse. Okay. So what is the value of B3? B3 is 11, that is not equal to 0. So we have to calculate the quotient. So quotient is 2. 11 to 22, so 4, so that is 11. So 26, what is divided is 11, 22, 4, so quotient is 2. Now calculate T1. T1 is A1 minus Q B1, A1 minus QB1. A1 minus QB1. Okay, A1 is 1 minus Q is 2 into B1 0. So that is 1. Okay. So A2 minus QB2. A2 is 0. 0 minus Q is 2 into B2 is 1. So that is minus 2. A3 minus QB3. So A3 is A3 is 26 minus QB3. B3 is 22. So that is 4. Right. So what we will do? We will do that B1, B2, B3 is equal to A1, A2, A3. So that is 0, 1, 11. Then 1 minus 2, and that is 4. 1 minus 2, 4. Now B3 is not 0 or 1. So we have to find out the quotient. So quotient is 2. Once again it is 2. So calculate T1. T1 is A1 minus QB1. So A1 is 0. A1 is 0 minus 0 minus Q2 into B1. 1. 0 minus 2 B1. So that is minus 2. Minus 2. And then here 1 minus Q2 4. 1 minus minus 4 plus 4, that is 5. So that is 5. And here that is A3 is 11 minus Q before that is not. That is 3. So now it will become B1 1 minus 2, then 4. It is minus 2, 5 and minus and 3. 3. Okay. So now 1. This is 1 minus QB1, 1 minus Q1, 1 minus QB1. So that is 2 becoming 3. Now it is T2 is A2 minus QB2. A2 is minus 2 minus 5. So that is minus 7. Minus 7. And 1 A3. It is 4 minus 3. 4 minus 3. 4 minus 3. 4 minus 3. 1. So now this is minus 2, 5, 3. And this is 3 minus 7. And this is 1. So now it is 1. It is 1 means both 11 and 26 are relatively prime. So the GCD of A and B is 1. So that is 26 and it is 1, and the multiplicative inverse is B. So B2 is the multiplicative inverse. That is 1. So multiplicative inverse in this case is minus 7. So minus 7 is 26 minus 7. So that is 19. 27 minus 10. Okay. So 19. Let's try. 19 into 11 is 19 into 11 9 209 mod 26 is equal to 1 1. So when 19 will multiply with 11 in the field of Galois wheel of 20 subscript 26, then so this is the process of extended Euclidean algorithm. Okay, so I hope you understood. Although you can contact me. Thank you.